Lesson 7.2 covers the topic of scientific notation. Scientific notation is something that you may have already worked some with in science class, but we'll be covering specifics and different concepts within scientific notation. Today we're focusing on writing numbers in scientific notation and standard notation. Standard is just the typical way that you're used to seeing numbers written, and then also being able to compare numbers using scientific notation specifically. And a couple strategies for that. Before we can do those, we have to define what scientific notation is. Scientific notation is the product of two numbers, or a number that's multiplied by a power of 10 that's an integer. So it looks something like this, where n, that exponent, is an integer, which means it's just a positive or negative whole number. And then a, so this first digit, a, is a number that is less than or equal, or 1 is less than or equal to a, and a is less than 10, meaning it's somewhere between 1 and 10. It could be 9.99. It could be the number 1 because of the or equal to. What that's pretty much saying is that a has to fit with one digit to the left of the decimal. A single digit whole number, but it also could have a decimal to it. It could be 1.011. It could be exactly 1, or it could be 9.989. However, it cannot be 10.1 because of the two digits. It cannot be 12.38 because of the two digits. It can only have one digit left of the decimal. Each of these examples would be good examples of scientific notation. One digit to the left of the decimal, or multiplying by a power of 10 with an integer exponent, either a positive or a negative whole number. Same thing for this one. Both of these fit all of that criteria. One digit to the left of the decimal, multiplying by a power of 10, and then a positive or negative whole number exponent. When you see this on your calculator, the E on your calculator, it just means scientific notation. So 1 and 35/100 e to the 8th power is the same thing as 1.35 times 10 to the 8th power. So that's something important to know. If you're trying to type in this on your calculator, you'd want to look for to the power of key. So our first step is to be able to recognize if it is scientific notation or not, and if it's not, explain using words as to why not. So when we look at this first one, we would say no, it is not scientific notation because of the 0. 0 is not between 1 and 10. Yes, it's a single digit, but it has to be at least 1. For B, if we look at the first one, there's one digit to the left of the decimal between 1 and 9. We're multiplying by a power of 10, and we have an integer exponent, meaning it's a positive or negative whole number. So yes, this would be correct scientific notation. If we look at the third one, C, yes, one digit to the left between the digits 1 and 9. We're multiplying, but not by a power of 10. We're multiplying by a power of 100, so we would be a no, must multiply by power of 10. Not 100. So this part would need to be rewritten to be in scientific notation. If we look at a few more, A doesn't have just one digit to the left of the decimal because the decimal would be right here. So this one would be a no automatically because it's not one digit left of the decimal. For B, it is one digit to the left of the decimal. We're multiplying by a power of 10. And it's okay to have a negative exponent as long as it's a whole number. So this one would be, yes, it is correct scientific notation. For C, we would say no, because that digit left of the decimal must be 1 through 9. Must be digit numbers 1 through 9. So it could be a 1, 2, 3, 4, 5, 6, 7, 8, or 9, but it cannot be a 0 and it cannot be 10 because it has to be one single digit. Okay, so that's being able to recognize if it's actually written in scientific notation. When it's not written in scientific notation, we have to be able to write it in scientific notation. Again, following those 3 rules. We want one digit left of decimal, numbers 1 through 9 possibly. We need to multiply by a power of 10. And we need an integer exponent. So, when we look at the first number, the approximate distance between the Sun and Saturn, here is our number. And it's written out as a normal large number. We use scientific notation to represent really, really long numbers, either a really large value or a really, really tiny value. But either way, the number is a long digit number, which this is. So the first thing we want to do is determine where that decimal is going to be. We know that there can only be one digit to the left of the decimal, and that digit has to be 1 through 9. So we would put our decimal right where that comma is, and we would say 1.43. All of these zeros don't give it additional value, so we don't need to write them. So that's our first part. We would say times 10, and then we need to count how many digits or how many times we would have to multiply by 10 to get it all the way back. So we would multiply it 3 times for each digit here. Each digit we'd move around the 4, the 3, and the 0, so that's 3 times there, another 3 times here, and another 3 times here. So we would move the decimal a total of 9 times, or we would have to multiply this by 10 a total of 9 times to get it back to the end of that number. So this would be our answer in scientific notation. We used a positive exponent because we're representing a really, really large number. You'll notice for B that the value of the number is a really, really small value. So we're going to end up using a negative exponent because of that. It's a good note to take down. Again, wanting to follow each of our 3 guidelines. We want one digit to the left of the decimal. That digit has to be numbers 1 through 9, so that one digit can't be any of these zeros. It would have to be this 1, meaning our decimal would have to go right here. So we're going to have 1 times 10, and then we have to determine our exponent. It's representing a very small value, so we know it's going to be negative. And now we have to determine how many times. Especially when there are all of these zeros, you want to double count and show some markings on your page to keep track of them. I'm going to go 3 at a time. 1, 2, 3, 4, 5, 6, 7, 8, 9 is to the left of the 1, so we need one more, and that's 10. 3, 3, 3, and then one more. So we have to the negative 10th power. Negative exponent, because it's a very, very small valued number. And that would be our answer in scientific notation. So let's do that for each of these two. We'll just do a couple of them. We'll just do A and B. So if we look at this one, we want one digit to the left of the decimal, so it'll be between the 6 and the 7. We don't need to write the zeros because they don't add additional value, but we know we're going to multiply by 10 to an exponent. It's a large number, or above 1, so it's going to be a positive exponent, and it's going from here, so we're going 1, 2, 3 places around the 8 and the 7, so we've got 3 here, 2 there, so it's a total of 5 times we had to move that decimal. So it's a positive 5 exponent. This decimal is a small value. It's a value less than 1. So we're going to use a negative exponent. Our decimal we want in between the 3 and the 2 because we have to have one digit between 1 and 9 to the left of our decimal. So we're going to have 3 and 2 tenths. We don't need the zeros here because it doesn't add additional value and we can only have one digit. And there's nothing after the 2. Then we determine how many times we move it. The decimal's here, so it's going to go 1, 2, 3, 4, 5. So it's going to be times 10 to the negative 5th power. We were going to the right, so it's to the negative 5th, and this is our answer. Then at times we'll also have to do the opposite, where we're writing a number in standard notation. Standard notation is just the typical way that you see numbers written. When they are expanded out, and you can read their value just as is. Again, this positive exponent represents a number larger than 1. This negative exponent represents a number less than 1. Or a small valued number. So in order for this number to become larger, we're multiplying by 10 6 times. So really what we're doing, when we multiply by 10 one time, it moves to the right once. We're not just doing it one time, we're moving it 6 times because of our exponent. So that's 1, 2, 3, 4, 5, 6. And we have to fill in those zeros in each spot. One time around the 5, and then 5 more times to get a total of 6. So then underneath that we would write it correctly with the commas in the correct place. 1, 2, 3, 4, 5 zeros. So this is our number in standard form. Positive exponent, so we moved it to the right because it was becoming larger. A negative exponent means that the decimal is getting smaller. We're going to move it or represent a smaller value. So instead of moving it to the right, now we're moving it to the left. If we were to move it one time to the left, that's like dividing by 10. That's one time. But we have to do 3 times, so it's 1, 2, 3 total. Fill in zeros and put our decimal in the correct place. Then underneath it, we want to write clearly what our number is, which would look like this. Be careful when there are a lot of zeros that you double check how many of them you have so you don't accidentally make a mistake. We'll do 2 more examples of examples like this. We'll do B and D. So if we look at B, we want to write it in standard notation. So we've got 4.6 times 10 to the negative 5th power. It's a negative exponent, so it's representing a really small value number. A smaller value would move our decimal to the left. So that's what we're going to do, and we're going to do that 5 times because the number is 5. 1, 2, 3, 4, 5. So we'll put our decimal there, fill in our 4 zeros before we put our 4 and 6. And that is our standard notation of B. If we look at D, we've got 3 and 8/10 times 10 to the 12th power. A much larger exponent this time, but it's still the same process. It's a positive exponent, so it has a large value. Larger than 3 and 8/10 would be multiplying or moving it to the right, and we're going to do that 12 times. This is where I'll write it underneath so that we can show that 12 times. 1 time around the 8, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You'll notice that 1 time was to get around the 8, and then 11 more times, so 11 zeros need to be added. And then we want to write it clearly underneath with our 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then double check. 3, 6, 9, 10, 11. 11 zeros. And then this would be our number in standard notation, that standard form. The next skill we're working on is being able to order the numbers using scientific notation. So you'll see that each of these numbers is written in scientific notation, or what may initially look like scientific notation, but not all of them are actually in scientific notation. We're going to first write each number in scientific notation before we order them from least to greatest. So we're going to do that directly underneath them so that everything is organized. To be able to do that for each one, we're just going to look at this first part. To write 49 and 7/10 in scientific notation, that's exactly what we were doing before. We want it to be 4.79, and we're giving it a smaller value. To get it back to 49, we have to multiply by 10. 4.97 times 10 would give us 49 and 7/10. So these two are the exact same. So then we're going to tag this on at the end, which gives us 4.97 times 10 to the second power because there's 2 of them. Okay. The next one happens to already be written in scientific notation. 1 digit to the left times 10 to an exponential, or to the power of 10. So that's already in scientific notation. For the next one, again, you'll notice that it's being multiplied by a power of 10, but it's still not in scientific notation. So again, we're going to write this first part in scientific notation. We want the decimal to be in between the 4 and the 7. And to get it there, we're going to be multiplying by a power of 10. However, we want this bottom value to be equivalent to this original value. And right now the value is larger. Because it's larger, it would need a negative exponent to bring it back down to a smaller value. So it's going to be a negative exponent. And it would move 1, 2 places. So it's a negative 2. So right now, this, if we were to write it out into standard form, expanded, it would go 1, 2 decimals over, which would match what we see up here. So because they are the same, then we can bring down our times 10 to the 9th. And then from there, combine these two together. We're multiplying by 10, negative 2 times, and by 10 again, 9 times, which gives us 4 and 7/10 times 10 to the 7th power. Then if we look at the last one, 495, it's written in standard form, so it's a little bit easier for us to write it. We want it to be between the 4 and the 9. We would move it 1, 2 times, so it's times 10 to the second power, because if we were to multiply by a positive 2, it would move it to the right, which would make it match. A negative would represent an even smaller value. So now that we have them written in scientific notation, We're going to put them in order by the power of tens. The exponents make a bigger difference or a bigger change in the value. So when we're comparing them, we start with those exponents. That's the first step in ordering them once they're in that scientific notation. So we've got our 4 now that we're comparing. And we want the smallest, because it's in order from least to greatest, the smallest exponents first. This is the times 10 to the second, times 10 to the 7th, times 10 to the 7th, times 10 to the second. So we've got 2 of them that would go first. So when we compare these two, then if they match, we look at the decimal parts. Then we compare their decimal parts. Well, 97 hundredths is larger than 95 hundredths, so 95 hundredths is the smallest. And then it's this one, so that's why this one's written first, and 4 95 hundredths times 10 to the second. Then 4 97 hundredths times 10 to the second. Then that leaves us with our 2 scientific notation numbers with times 10 to the 7th power. Because their exponents match, but they're the biggest exponents, now we compare their numbers. Well, 17, or 1/10, is smaller than 7/10, or we could say 17 hundredths is smaller than 70 hundredths, so this one would be next, followed by the largest value. So we can put them in order. But again, our final answer should always be in the original form, which is why we kept all of our information organized, so then we can write it back into the original form. 4 95 hundredths was originally 495. 4 97 hundredths times 10 to the second was originally 49 and 7/10 times 10. And so on, all the way through to put them in order, and then this would be your final answer. The final examples that we work on are when we need to multiply 2 different scientific notations or different values and then have the final answer in scientific notation. You'll notice that the only operation happening in this entire problem here, this first one, is multiplication. 3 times 10, this is multiplication. 10 to the 5th, that's repeated multiplication, times 10 times 10 times 10, and so on. Parentheses back to back, that's also multiplication. This is multiplication, and again, our power of 10 is again multiplication. It's all multiplication. So what that means is we can use our commutative property to change the order of what we're multiplying to make it a little bit easier. So what we're really going to do is put the 3 times the 4 next to each other, because they're just our simple lonely numbers, 3 times 4 then. And then we're also going to have that times 10 to the 5th times 10 to the 7th. They're similar, so we put them together as well. Then from here, we know what 3 times 4 is. That's 12. Times, and here it's 10 to the 5th, so we're multiplying by 10 to the 5th, and we're also multiplying by 10 to the 7th. So in all, we're multiplying by 10 a total of 12 times. For right now, it's still not scientific notation because of this first number. So we need to adjust this first number by writing just the 12 in scientific notation. That would be 1 2/10 times 10. Because 1 2/10 times 10 gives us 12. They're equal. But we can't forget about the times 10 to the 12th. So in the end, we have 1 2/10 times 10 to the 13th power for our final answer in scientific notation. If we do that same thing for number 2, we have 1.5 times 4. Those are our lonely numbers, so we'll put them next to each other. And then we also have the times 10 to the third and the times 10 to the negative 7th. Again, they are similar, so they'll be grouped together. But it's still all multiplication. We just changed the order of what's being multiplied. 1.5 of 4 would give us 6, because 1 times 4 is 4, and half of 4 is 2, so 2 plus that 4 is 6, times, and then we have to figure out how many total times are we actually multiplying by 10. 3 times here and negative 7 times here. So in all, we're going to add those exponents together for a total of negative 4 times. So times 10 to the negative 4. Be careful to remember to put that times 10 in there, because sometimes it's an easy thing to forget. In this case, this is already scientific notation because the 6 is just one single digit. We're going to jump down and do the last one, the last problem. You'll notice this time that it's only one scientific notation and then just a single number. But we still have numbers that are similar. The 7 is still being multiplied in, which is still being multiplied by the power of 10, which is also multiplication. So what we're going to do is multiply these two similar numbers together by changing that order and just having it 7 times 3 1/10. And then from there, we're going to multiply by 10 to the negative 4th. We can show that over here if we need to, which gives us 21 7/10 times 10 to the negative 4th. It looks like scientific notation, but we learned in this lesson that it is not because of the 21 7/10. So we'll need to rewrite this number as 2 17/100, but we want it to have the same value. We want them to be equal. So to bring this 2 back up to 21, we would need to multiply it by 10, and now they are equivalent. Notice it's a 10 to the positive 1 exponent. This is still here, so we still have to say times 10 to the negative 4th, but then we can use this to combine those exponents, giving us 2 17/100 times 10 to the negative 3rd power as our final answer. So using that commutative property of multiplication is really helpful when we're working on this. Again, the main focus was to be able to write the numbers in scientific and standard notation and be able to compare the numbers using scientific notation within each of those different types of examples.